Okay, let's unpack this. Have you ever looked at the periodic table, that chart from science class? It's so familiar. And found yourself wondering if it truly captures all the forms of matter, like everything in this huge universe.
Mm.
What if there's an entire realm of existence, beyond what those neat squares represent? Something far stranger, maybe more complex than we can even imagine right now.
Right.
Today, we're embarking on a really fascinating deep dive into exactly that. Matter beyond the periodic table. We'll be exploring some truly mind-bending concepts, and we're drawing heavily from some groundbreaking theoretical work. Specifically, Philip Randolph Lillian's papers and notes on Beyond the Periodic Table and his revolutionary HHCR
Yeah, and our mission for you today is to journey beyond the conventional. We want to help you understand the fundamental limitations of our standard atomic model, you see. Then we'll delve into some real and hypothetical exotic states of matter, things that sound like science fiction, but might be real. And then the goal is to grasp a unifying framework that tries to make sense of it all. Lillian's hypersymmetry coherence and hypersymmetry reduction theory of everything, or HHCR for short.
HHCR, got it.
Prepare for some truly illuminating aha moments, I think. Moments that might just redefine how you think about reality itself.
I'm ready. So let's start with the familiar, the periodic table. We all grew up with it.
Absolutely.
It's like the bedrock of chemistry. It charts the elements based on their atomic structure, different numbers of protons, neutrons, electrons.
Yeah. Defines how they interact.
Exactly. It
Yeah.
forms everything from, the air we breathe to the phone in your pocket. But elegant, it's powerful, it grounds so much of our science.
It really does. It's an incredible achievement.
But as you hooted, for all its power, its utility,
Yeah.
it operates within certain boundaries, doesn't it? Very specific ones.
Exactly. And that's the fascinating part. The remarkable thing about the periodic table is its design, but that very design also creates its inherent limitations. You see, it fundamentally assumes matter is mostly made of these standard subatomic particles we know, protons, neutrons, electrons.
Right. The usual suspects.
The usual suspects. And it assumes their interactions are governed, almost exclusively, by the electromagnetic force and quantum mechanics, all happening within our familiar 3D spacetime.
Okay.
Think of it like a beautifully precise map, maybe a nautical chart. It's fantastic for navigating the known oceans. But it doesn't show you what's on land or what's flying above, or maybe even what's in a different dimension entirely.
So it's a great map for a specific territory.
Precisely. A powerful lens, but it's definitely not the only lens to view matter through.
So what does this all mean for what it can't account for? What kinds of matter, what forms of existence simply fall outside this chart, this, otherwise comprehensive chart we've relied on for so long? It really makes you wonder what else is out there, hiding in plain sight, perhaps.
It absolutely does. And that's where the real mystery begins, I think. The periodic table, despite its incredible success, simply cannot account for entire categories of matter that deviate, sometimes profoundly, from this standard atomic model.
Okay, like what?
Well, first we're talking about matter that could be composed of entirely alternative particles. Not just, different numbers of protons and neutrons making a super heavy element, but something built from fundamentally different building blocks altogether.
Wow, okay. Building blocks not even on our list.
Exactly. Imagine Lego bricks we didn't even know existed. Second, it can't really describe matter that only exists in truly extreme environments.
Extreme how?
Think conditions so incredibly dense, or hot, or cold, so far removed from anything on Earth or even inside our sun, that they fundamentally change how matter behaves, how it constitutes itself.
So under that kind of pressure or temperature,
The very idea of an atom, as we know it, might just dissolve. It ceases to be meaningful, giving way to entirely new states of being, new forms of matter.
okay, that makes sense.
And third, and this is perhaps the most mind-bending part, it cannot account for matter manifesting through entirely different physical principles. Principles that might not rely on electromagnetism, the very force that dictates the table structure.
So not just new elements at the bottom.
No, this isn't just about undiscovered elements that might fit into row 8 or 9 someday. We're talking about entirely different kinds of matter. Forms of existence that our current classification system, the periodic table, it just isn't designed to recognize or describe.
Right.
It's like having a detailed chart of all known fruits and vegetables and then discovering rocks that can reproduce or maybe solidified sunlight that has mass. They just don't fit the categories.
Okay, here's where it gets really interesting then and starts to stretch the imagination. Because Our sources, Lillian's work especially, give us some incredible examples. Matter that seems to defy the periodic table, pushing the boundaries of what we currently understand.
Hmm.
Whether it's stuff we actually see in labs or theorize about in deep space or things that are purely hypothetical for now, it's like looking at a familiar constellation and suddenly realizing there are unseen galaxies hiding behind it.
That's a great analogy. And yet, let's begin with states that are either observed, maybe under extreme conditions, or actually created in laboratories. These really showcase how matter can exist without those typical atomic structures. First up, let's talk about quark matter.
Quark matter. Okay.
Now, usually in our everyday world, quarks are always locked up tight, right? Forming protons and neutrons inside atoms.
Right. They're never seen alone.
Almost never. But imagine matter where these fundamental quarks, the tiny bits inside protons and neutrons, aren't bound together. They exist in a free, deconfined state.
Like a soup, a quark soup.
Exactly. And this even includes something called strange quark matter, where strange quarks, which are usually heavier and less common, become stable and numerous. This kind of stuff is theorized to exist in the incredibly dense cores of neutron stars.
Where gravity is just immense.
Unimaginably immense.
Oh.
It crushes atoms, crushes nuclei, potentially freeing the quarks. Or we might glimpse it for fleeting moments in high-energy particle collisions, like at the LHC. It's a completely different way for matter to organize itself.
Fascinating. What else?
Then we have Bose-Einstein condensates, or BECs for short.
Ah, yes, BECs. I've heard of those. Super cold, right?
Extremely cold. You form them by cooling particles, often whole atoms, down to near absolute zero, just a tiny fraction of a degree above the coldest possible temperature.
And what happens then?
Something really weird and wonderful.
Mm.
The particles stop behaving like individuals. They lose their distinct identities and sort of collapse into a single quantum state.
Mm.
They effectively become one unified quantum wave, a single superatom.
Wow, so they all act in perfect unison.
Perfect unison. It's a profound shift from typical atomic structures, where atoms are distinct and bouncing around. It's like, imagine a crowded room of people all suddenly deciding to move and think as one single entity.
A bit creepy, but I get the idea.
Yeah, maybe a little. They were theorized way back in the 1920s by Einstein and Bose, but only created in labs in the mid-90s. A huge achievement, opening a whole new window into quantum weirdness.
Okay, and similar to that.
Similarly, we have fermionic condensates. These are kind of analogous to BECs, but they involve fermions, particles like electrons or protons, which have different quantum rules than bosons.
What's the difference?
Well, fermions obey the Pauli exclusion principle. Basically, no two identical fermions can be in the same quantum state at the same time. They like their personal space.
Okay, so how do they condense?
You have to trick them, essentially. Usually by getting them to pair up into something called Cooper pairs. These pairs then can act like bosons and condense. They also happen at extremely low temperatures, and they're really important for understanding things like superconductivity. Again, it's quantum coherence without forming traditional atoms.
Right, another way matter exists beyond the table.
Exactly. Moving on, let's talk about quark-gluon plasma.
Okay, that sounds intense. Plasma, but with quarks and gluons.
You got it. If quark matter is a dense soup of quarks, imagine this is an even hotter, denser soup that probably existed just microseconds after the Big Bang.
Wow, the dawn of time.
Pretty much. It's a super high energy state where quarks and gluons, the particles that normally glue quarks together inside protons and neutrons, are no longer confined. They just flow freely, like a liquid.
So like the universe before atoms even formed.
Precisely. It's a state that mimics the conditions of the very early universe. And scientists have actually managed to briefly recreate it in particle accelerators by smashing heavy ions, like gold or lead nuclei, together at incredible speeds.
Incredible. We can make primordial soup.
For tiny fractions of a second, yes.
Yeah.
Gives us a direct glimpse into that primal state of matter.
Amazing. And you mentioned one more in this category.
Yes, neutronium. This is the stuff you find in neutron stars, the collapsed cores left behind after massive stars go supernova.
Ah, yes.
Super dense, incredibly dense.
Yeah.
As the name suggests, it's composed almost entirely of neutrons, packed shoulder to shoulder, without any traditional atomic structures. Imagine a star made almost purely of neutrons. It's truly astounding.
How does that happen?
The gravity inside a neutron star is so immense it overcomes the forces that keep atoms structured. Electron shells collapse, and protons and electrons are basically forced to merge into neutrons. Crushed together. The result is this uniform, unbelievably dense neutron soup. A single teaspoonful of neutronium could weigh billions of tons on Earth.
Billions of tons. It's hard to even wrap your head around that.
It really is.
Huh.
It's perhaps the ultimate example of matter compressed beyond all recognition, completely outside the bounds of the periodic table.
Okay, so those are states we've observed or created. But then, as you said, we venture into the realm of the truly theoretical, hypothetical particles, strange structures, stuff that really stretches our imagination about what matter could be.
Right, and this is where things get even more speculative, but also potentially more profound. It raises this crucial question. What if the majority of the universe is made of matter we can't even detect directly? Or matter that behaves in ways we haven't even conceived of yet?
A hidden universe, almost.
In a way, yes. One fascinating category here is super heavy elements. These are elements way beyond Oganesson, element 118, which is currently the heaviest known element on our table.
You've made those, haven't we? But they don't last long.
Exactly. Scientists create them in labs, smashing lighter elements together, but they typically exist for vanishingly small fractions of a second before they decay radioactively. They're incredibly unstable.
So fleeting glimpses.
Right. But here's the intriguing part. There's a theoretical prediction of an island of stability.
An island of stability. Sounds nice.
Doesn't it? The idea is that for certain isotopes of these super heavy elements, specific sort of magic combinations of protons and neutrons could grant them a surprising degree of stability. Maybe not permanently stable, but perhaps living for seconds, minutes, even years.
Long enough to study. Or maybe even use.
Potentially. It's like finding a calm, stable oasis in a sea of extreme radioactivity. Finding this island is a major goal in nuclear physics.
Okay, that's fascinating. What else is theoretical?
Well, then, of course, there's the big one, dark matter.
Ah, yes. The universe's missing mass.
Precisely. This is one of the absolute biggest mysteries in cosmology today, and frankly, one of the most compelling reasons to look beyond the periodic table. It makes up the vast majority of the universe's mass, maybe 5 or 6 times more mass than all the ordinary matter, all the stars and galaxies and us put together.
5 times more.
Wow, yeah. Yet, crucially, it is not composed of standard atomic matter, protons, neutrons, electrons, which is exactly why it falls outside the periodic table.
You can't see it, touch it.
Nope. We can't see it directly. It doesn't interact with light or any electromagnetic force, but its gravitational effects are undeniable. We see galaxies rotating faster than they should, gravitational lensing, bending light around invisible clumps. It's shaping the entire cosmos on large scales.
Oh, what could it be?
That's the million-dollar question. Candidates include things like WIMPs, weakly interacting massive particles, or maybe axions, another hypothetical particle. The idea is this WIMP matter, for instance, could form huge, massive clumps, halos around galaxies, but without any electromagnetic interaction, making it totally invisible to us.
Passing right through us.
Literally passing right through the Earth and us, right now, probably, without leaving a trace. Trying to detect it directly is one of the biggest challenges in physics, like trying to study a ghost.
Okay, dark matter. What other theoretical wonders?
Well, there's also Rydberg matter. This isn't entirely new particles, but involves atoms, regular atoms, that are pushed into highly excited states.
Highly excited.
Yeah, where their outermost electron orbitals become incredibly large and diffuse. Think of an atom puffing itself up to enormous size like a giant fluffy cloud.
Okay.
In these states, these puffed up atoms can interact in really novel ways, forming unusual, often loosely bound, diffuse structures. They exhibit very strange properties, sometimes with very long lifetimes, hinting at new kinds of chemical bonding or material states.
Interesting. Not quite an element, but not normal matter either.
Exactly. Then there's positronium. This is fascinating. It's a bound state of an electron, and its antimatter counterpart, the positron.
Matter and antimatter together, doesn't that just annihilate?
It does, very quickly. But for a fleeting moment, it exists as a sort of atom, an electron orbiting a positron. It behaves like matter, it has energy levels, but it's not an element on the periodic table because there's no nucleus with protons and neutrons.
So it's like a temporary exotic atom made of opposites.
You could put it that way. A clear example of matter existing outside our standard elemental classification, even if it is incredibly short-lived.
Okay, now, are we getting into really weird territory?
We can definitely go weirder. Venturing deeper into pure hypothesis, we have tachyons.
Faster than light particles.
That's the theory. Hypothetical particles theorized to always travel faster than light.
Yeah.
If they exist, and that's a huge if, they would inhabit a completely different causal regime. Time might run backwards for them. Cause and effect could be reversed.
Whoa.
Yeah. and they could potentially form unknown types of matter that don't obey the same physical laws as us slowpokes limited by the speed of light. Their very existence would challenge our fundamental understanding of causality and space-time. It's a truly wild concept, right on the edge of theoretical
It's
possibility.
mind-bending, for sure.
Then there are magnetic monopoles.
Single magnetic poles,
Yeah.
like a north without a south.
Exactly. All known magnets, from fridge magnets to the Earth's magnetic field, always have both a north and a south pole. Cut a bar magnet in half, you get two smaller magnets, each with both poles. But theory suggests particles could exist with just a single magnetic charge, a pure north or a pure south.
Have we found any?
Not definitively, despite many searches. But if they were found, it would fundamentally change our understanding of electromagnetism. Maxwell's equations would need an update. And they could potentially form entirely new structures, maybe a kind of magnetic chemistry not accounted for in our current system.
Magnetic chemistry. Wow. Okay, what else?
Another theoretical entity linked back to quark matter is stable strangelets.
Strangelets, like little bits of strange quark matter.
Kind of. They're described as potentially stable clumps of quark matter containing roughly equal numbers of up, down, and strange quarks. Unlike individual strange quarks, which are unstable, these theoretical clumps, or strangelets, could be incredibly stable, maybe even more stable than ordinary atomic nuclei like iron.
More stable than iron. That would be profound.
They would be huge. If they exist, they could have massive implications for astrophysics. Maybe neutron stars are actually strange quark stars, and for particle physics. They represent a potential new fundamental state of matter.
Okay. And Lillian mentions even more speculative stuff too, right?
Oh, yes. He touches on some incredibly speculative forms in his work. For instance, he talks about synthetic matter. This isn't naturally occurring, but includes things like metamaterials.
I've heard of those. Like invisibility cloaks.
That's the popular idea, yeah. Metamaterials are engineered materials, usually with structures smaller than the wavelength of light or sound they interact with. This structure gives them unnatural properties, bending light backwards, like we discussed with negative refraction, potentially leading to perfect lenses, or, yes, rudimentary invisibility cloaks.
So matter designed by us to break the usual rules.
Exactly. And along similar lines, artificial atoms. These aren't elements, but things like quantum dots, tiny semiconductor crystals, or other nanostructures that are engineered to mimic the behavior of atoms, or even possess properties that no natural atom could have. Again, human-made constructs pushing the boundaries of what matter can be and do.
Engineered matter.
And then, perhaps the most mind-bending of all, Lillian speculates on the profound concept of matter in alternate universes.
Whoa.
Here, he suggests that if other universes exist, perhaps in a multiverse scenario, and if they have different fundamental physical constants, maybe gravity is stronger there, or the charge of the electron is different, or there are 4 spatial dimensions instead of 3.
Then matter itself would be different.
Completely different. Their fundamental matter structures could be entirely distinct from ours. They might have their own version of a periodic table, but with completely unknown rules, elements, and interactions. Imagine a universe where atoms simply can't form stably, or where entirely different forces dominate. It's the ultimate beyond the periodic table scenario.
It really puts our familiar table in perspective, doesn't it? Just one possibility among maybe infinite variations.
Exactly. It's a humbling thought.
So these diverse examples, from quark soup to alternate universes, they all point to a cosmos that is far richer, far more complex, maybe far stranger than our standard periodic table alone can describe. It really makes you think about how much more there is out there beyond our familiar atomic neighborhood. And this is precisely where Philip Randolph Lillian's incredible theoretical framework, the HHCR TOE, comes into play, right? It's not just listing weird stuff. It's proposing a way to maybe unify it all.
Precisely. Philip Randolph Lillian, the originator of this HHCR TOE hypersymmetry, coherence, and hypersymmetry reduction theory of everything, proposes it as a fundamental unifying theory. The goal is to understand these exotic forms of matter, their unique properties, and maybe even the standard matter we do know, all through a radically different lens.
A theory of everything. That's ambitious.
Extremely ambitious. Instead of just adding new particles or forces piece by piece to fix problems in the standard model, his framework seeks a deeper, potentially more elegant explanation for, well, everything we observe and theorize about.
Okay, so let's dive into the core concepts of this HHCR TOE. What's really at its heart? What's the fundamental shift in thinking he's proposing here?
The absolute foundational idea, the core shift, is this. Lillian's framework suggests that matter, as we perceive it, might not be truly fundamental in the way we usually think. not made of tiny immutable building blocks like quarks or electrons being the absolute bottom layer.
Okay. So what is it then?
Instead, he proposes that matter is an emergent phenomenon. It arises from deeper invariance, specifically from something he calls hypersymmetry coherence.
Emergent, like wetness emerges from water molecules but isn't a property of a single molecule.
That's a good starting analogy, yes, but much more profound. Imagine, instead of your hand being made of tiny, solid Lego bricks, imagine it's an intricate, stable pattern arising from a universe teeming with hidden, vibrating symmetries, like a complex, persistent knot formed from an infinitely long vibrating string.
So matter isn't the stuff, it's the pattern.
In this view, yes. Matter is not primary, but a manifestation, a stable resonance, emerging from a more profound underlying principle, a result of deep cosmic harmonies and symmetries. It really challenges the very notion of what matter is.
Wow, okay. And central to this, you mentioned hypergravity.
Yes, absolutely central is the concept of hypergravity as the invariant foundation. Lillian argues that hypergravity is the true underlying fundamental strength. It's not the weakened gravity we experience daily, the force holding us to Earth or keeping planets in orbit. That familiar gravity, he posits, is merely a reduced, weakened shadow of this much more potent fundamental force.
So the gravity we feel is just the tip of the iceberg.
Exactly. Hypergravity is the iceberg. It's proposed as the invariant foundation of his entire theory of everything, the HHCR2E. And understanding it is critical to understanding matter beyond the periodic table. Lillian posits that all other forces, and indeed matter itself, might ultimately derive from this primal hypergravity and its symmetries.
All forces, electromagnetism, nuclear forces, all from hypergravity.
That's the proposal. It aims to provide a coherent framework for phenomena that standard physics struggles with, suggesting that what we consider normal physics is just one particular manifestation, one reduced symmetry state within a much grander hypergravitational scheme.
Okay, let's unpack this more. The sources mention hyperfractal layers and resonance loci. Those sound incredibly complex. How do these abstract concepts tie into matter actually emerging, especially this non-periodic matter? Can you maybe give us another analogy?
Sure, let's try. Think of hyperfractal layers as nested, self-similar structures existing across different dimensional scales. Imagine a fractal pattern like the Mandelbrot said, but extending not just in 2D but into higher dimensions, with intricate structures appearing at every level of zoom, potentially infinitely.
Okay, nested dimensions of complexity.
Kind of, yes, and resonance loci. Imagine these as specific points or conditions of energetic harmony within these hyperfractal layers, like finding the exact spots on a complex vibrating surface where sand grains will gather to form stable patterns, the Clatomy figures. These loci are points of stability, of coherence.
So stable points in these complex layers.
Right. Within the HHCR2E, matter, especially these exotic forms, can emerge through these hyperfractal layers at specific resonance loci. The crucial idea is that this emergence is inherently tied to hypergravity coherence and hypersymmetry reductions.
Okay, and what does that imply about how this matter would behave?
It implies several really profound things. First, such matter might literally exist in higher dimensions and project aspects of itself into our lower dimensional space.
Yeah.
Think about Plato's cave, or the classic flatland analogy.
We're only seeing the shadow.
Exactly. A complex 4D object passing through our 3D world might appear as a changing 3D shape. What we perceive as familiar or even exotic matter could be just a limited lower dimensional projection of a richer hyperdimensional reality.
Okay, that's one implication.
Second, such matter could be governed by coherence conditions rather than conventional quantum field dynamics. Its behavior wouldn't just be the sum of individual particle interactions described by quantum fields. Instead, it would be dictated by a unified, stable state related to its underlying hypersymmetry and connection to the hypergravity field, more like a single coherent wave than a collection of particles.
Governed by harmony, almost.
You could say that. Which leads to the third point. It could exhibit harmonic relationships dictated by resonance loci and coherent resonance fields. Different forms of matter might arise or become stable only at specific resonant frequencies or points of vibrational harmony within these hyperfractal layers. Like tuning forks resonating together, certain forms of matter might coalesce only where these hyperdimensional vibrations achieve a perfect, stable harmony.
So matter prefers certain notes in this cosmic symphony.
A very poetic way to put it, yes. And finally, fourth, it could arise from novel symmetries where lower dimensional symmetries are seen as higher dimensional asymmetries. This is radical. What we perceive as a fundamental force or symmetry in our 3D world, like electromagnetism, might just be a broken or reduced aspect of a much grander, unified symmetry existing in higher dimensions, rooted in hypergravity.
Broken symmetry. Like a pattern that's almost perfect, but slightly flawed from our perspective.
Kind of. Imagine seeing only a fragment of a perfectly symmetrical object. The fragment itself looks asymmetrical, but the underlying object is perfectly symmetrical. Our familiar forces might be like those fragments.
Okay, and this relates to gauge symmetries.
Precisely. Building on that last point, Lillian's framework makes this truly radical claim that gauge symmetries, which are the mathematical foundation governing our known fundamental forces electromagnetism, the strong and weak nuclear forces actually emerge as asymmetries from hypergravity.
So our fundamental rules are broken versions of a deeper rule.
That's the core idea. It's a profound conceptual shift. What we see as the laws of our universe, the forces shaping atoms and light, might not be fundamental in themselves. They could be reduced manifestations of a deeper, unified hypersymmetry rooted in hypergravity.
And the implication of that?
The implication is huge. Entirely new force carrier particles could exist, mediating interactions for this non-periodic matter. Particles that don't fit into our current standard model because they operate under different higher dimensional symmetry rules or interact in ways that reflect the more fundamental unbroken symmetry. It's like discovering that the rules of checkers are just a simplified version of an infinite, cosmic, multidimensional game.
Okay, my mind is officially bent. So if matter itself is emergent and our forces are just shadows of hypergravity, what does this mean for how this non-periodic matter would actually behave? How would it interact with the universe we know? With gravity, light, the nuclear forces, it can't be the same as regular matter, right?
Absolutely not. It would behave very differently. And this is where the HHCR TOE provides some really profound, testable predictions, predicting distinct, often counterintuitive interactions with the forces we thought we understood. It really challenges our everyday experience of physics.
Okay, let's start with gravity. How would it interact gravitationally?
Right, gravitational interactions. What's fascinating here is the idea of hypergravity coupling. Lillian suggests non-periodic matter could display gravitational effects far stronger than you'd expect just based on its apparent mass or energy.
Stronger gravity than it should have.
Potentially, yes, because it might retain a more direct, potent link to that underlying fundamental hypergravity field, a link that ordinary matter has largely lost through symmetry reductions. This could manifest as, say, a highly localized, intense gravitational pull around an object that otherwise seems small or low mass.
Like a hidden density.
Or perhaps unique behavior under extreme conditions, like near black holes or inside neutron stars. Those environments might allow these hypergravitational effects to become much more obvious, giving us a chance to maybe observe them.
And it might bypass the weakness of gravity we normally see.
Exactly. That's the idea of reduced gravitational weakness. Unlike ordinary matter, where gravity seems incredibly feeble compared to electromagnetism or the nuclear forces, remember, a tiny magnet can lift a paperclip against the Earth's entire pull.
Right.
Non-periodic matter might retain hypergravity's inherent strength. It bypasses the symmetry reductions that dilute gravity in standard physics. This means its gravitational influence could be much more significant relative to its mass than anything we typically see. It could be a major source of gravity in the cosmos, even if we can't detect it otherwise.
A potential link to dark matter's gravity, perhaps.
That's certainly a tantalizing possibility raised by the framework. And we might also see anomalous inertia.
Anomalous inertia. Inertia is just resistance to change in motion, right? Mass.
Usually, yes. But hyperdimensional matter, interacting with hypergravity coherence, could exhibit inertia that varies. Its resistance to acceleration or deceleration might not be a fixed constant like Ephemer suggests for ordinary objects.
Its mass could change.
Its inertial mass could appear to change, depending on its interaction with these underlying coherence fields. This could lead to phenomena Lillian calls inertia modulation.
Manipulating inertia. That sounds like something pulled directly from a futuristic space opera. If you could control inertia, you could accelerate almost instantly, stop on a dime, without the crushing G-forces.
Indeed. Or imagine a spacecraft that could effectively change its inertial mass to navigate gravitational fields more easily. That's truly mind-bending stuff, pointing towards incredible, almost unimaginable technological possibilities if true.
Okay, inertia modulation. Wow, what about electromagnetism? That governs so much of our reality.
Right. Electromagnetic interactions. Light. Magnetism. Chemistry. It's all electromagnetism. But Lillian's work suggests it might work very differently for non-periodic matter. Maybe it doesn't interact electromagnetically in the conventional way at all.
How so?
Well, again, Lillian explains that hypergravity coherence is foundational here. It dictates the electromagnetic behavior of non-periodic matter within the HHCR toe, leading to truly unique properties that would likely defy Maxwell's equations, our standard rules for E&M.
Okay, like what kind of unique properties?
Consider altered charge behavior. Non-periodic matter might not possess the standard quantized electric charge we're used to, like the precise charge of an electron or proton. Instead, maybe it could have fractional charges.
Charges less than an electron's charge.
Exactly. Or perhaps hidden charges that are only detectable or manifest in higher dimensions. Imagine particles where the charge isn't fixed but is a more fluid dynamic property.
It could change.
It could fluctuate dynamically, potentially, depending on the coherent state of the surrounding hypergravity field. This might lead to phenomena like charge pulsation, where the apparent charge shifts over time, or maybe charge re-emergence, where a seemingly neutral object suddenly manifests charge due to a shift in its underlying hypersymmetry state. Very strange behavior.
Definitely strange. And magnetism.
Then you have non-Maxwellian magnetism. Magnetic fields generated by this stuff might not fully obey Maxwell's equations. Their behavior would reflect those deeper hypergravity-induced asymmetries we talked about.
So magnetism working by different rules.
Potentially. For example, this framework might naturally allow for magnetic monopoles, those particles with just a single north or south pole. Hypothetical in standard physics, but maybe a natural consequence here. Or you could have hyperdimensional magnetic fields, where the field lines and interactions involve components extending beyond our observable 3D space. This could affect field strength and direction in ways we can't currently predict or measure easily.
Leading to
Maybe high coherence magnetism. Ultra-stable magnetic fields that don't decay or fluctuate like normal fields, perhaps enabling powerful levitation or magnetic shielding far beyond what even superconductors can do today.
Okay. And how would it interact with light, with electromagnetic waves?
Another fascinating area. Anomalous absorption emission and negative refraction. Non-periodic matter could interact with light or other EM waves in highly unusual ways.
How unusual.
It might selectively absorb or emit very specific wavelengths based on its resonance loci, essentially being tuned to interact only with certain frequencies dictated by its hyperfractal structure, like a hyperselective antenna or filter.
Okay.
Even more dramatically, it could exhibit negative refractive indices.
Negative refraction. Light bends the wrong way.
Exactly. When light enters a normal medium like glass or water, it bends towards the normal line. With a negative index material, it would bend the other way, away from the normal, in a counterintuitive fashion.
And the implications of that.
Revolutionary technologies. Perfect lenses that could see details smaller than the wavelength of light, overcoming the diffraction limit. Or, yes, potentially true invisibility cloaks that could smoothly bend light around an object, rendering it undetectable.
Like in science fiction.
Just like in science fiction. Lillian even suggests electromagnetic waves might literally leak into higher dimensions when interacting with such matter. We might observe this as unexpected wavelength shifts, strange polarization effects, or even light just seeming to disappear under certain conditions.
Light leaking into other dimensions. Wow.
And finally, under electromagnetism, Lillian suggests photonic coherence. This type of matter might be able to stabilize the coherence of photons, light particles. This could potentially enable things like perpetual quantum entanglement, where particles stay linked no matter how far apart, or even self-sustaining laser systems that wouldn't need continuous energy input once started.
Self-sustaining lasers. Perpetual entanglement. The mind boggles. Okay, what about the nuclear forces? The strong and weak force that hold atoms together and govern decay.
Right, the strong and weak nuclear forces. Their behavior could also be profoundly different. For the strong force, which binds quarks into protons and neutrons, we might see strong force variants.
Different versions of the strong force.
Or at least matter composed of exotic quarks, not just up and down quarks, but maybe including strange, charm, bottom, or top quarks in stable configurations might experience the strong force differently, or interact with it in non-hadronic ways, meaning not forming standard protons or neutrons at all.
Supporting things like those stable strangelets you mentioned.
Exactly. Potentially supporting stable quark-gluon structures that we just don't see in ordinary matter. Entirely new nuclear configurations governed by modified strong force rules.
Okay. And the weak force. That's involved in radioactivity, right?
Yes, the weak force governs radioactive decay and certain particle transformations. Here, we might see reduced weak interactions.
Non-periodic matter might have a much lower tendency to undergo weak interactions, perhaps due to increased coherence from the hypergravity field, or maybe it has access to alternate decay pathways tied to higher dimensions. This could result in exceptionally stable forms of matter, things that just don't decay radioactively, like heavy elements we know, or forms that are essentially immortal.
Immortal matter.
And furthermore, when it does decay via weak interactions, it might produce alternate decay products. Not the usual electrons, neutrinos, etc., but maybe exotic types of neutrinos, or even particles that exist only in higher dimensions, completely outside our standard model. This could open up entirely new ways to probe the universe's fundamental structure.
Okay, beyond the four forces, are there other weird properties Lillian predicts?
Oh, yes. There are other key interactions and properties that really push the boundaries. For instance, quantum field interactions. Non-karyotic matter might exist in a kind of perpetual quantum coherent state. Its entire structure might behave like a single uncollapsed quantum wave function.
So it never settles down into one definite state.
Perhaps. Which means its interactions with observers, or with measuring devices, might be drastically different from ordinary quantum mechanics. The very act of trying to measure it might change it in unique ways, or it might resist collapse altogether. This could force us into new interpretations of quantum measurement theory, blurring that line between the observer and the observed even more.
Quantum mechanics is already weird enough.
Tell me about it. Then there are potential thermal and mechanical properties. If hypergravity coherence is dominant, such matter might exhibit thermal insensitivity.
It doesn't care about temperature.
It might not absorb or emit thermal energy in the standard ways. This could lead to temperature-invariant materials, things that remain completely unaffected by extreme heat or cold. Imagine building probes to fly into the sun, or structures that work perfectly at absolute zero.
That would be revolutionary for engineering.
Absolutely. And beyond that, these unique hyperdimensional structures could grant materials extreme hardness or elasticity or resistance to deformation far beyond anything conventional chemistry allows. Think literally indestructible materials, or things that can bend infinitely and snap back perfectly because their structure isn't based on chemical bonds, but on these deeper symmetries.
Unbreakable, temperature-proof materials.
Okay.
And finally, you mentioned interactions with dark matter and energy.
Yes. This is highly speculative, of course, but truly profound if correct. Lillian suggests interactions with dark matter and energy. Non-periodic matter might interact with dark matter directly, perhaps through these hyperdimensional fields or resonance loci. It could act as a kind of bridge or a missing link between the baryonic matter we know and the mysterious dark matter realms.
A way to finally see dark matter?
Potentially, or at least interact with it in a new way. And moreover, hypergravity coherence might allow non-periodic matter to tap into dark energy fields, that mysterious force driving the universe's accelerating expansion.
Tap into dark energy. For what?
Well, theoretically, for advanced energy manipulation or propulsion technologies, this is where you really get into the realm of star drives, manipulating the fabric of space-time, harnessing the universe's expansion energy, truly the stuff of far future science fiction, but grounded, in Lillian's view, in these fundamental principles of hypergravity and coherence.
This entire theoretical framework, HHCR TOE, with all these radical implications for how matter behaves, how forces work, it truly pushes the boundaries of our imagination. It makes you realize just how limited our current picture might be.
It really does.
But okay, let's bring it back down to Earth, slightly. What are the potential real-world implications if we could actually understand and maybe someday harness these principles of non-karyotic matter and hypergravity coherence? What kind of revolutionary technologies could actually arise? Beyond the grand theories, how could this translate into practical applications?
It's a great question. And the potential technological advancements are indeed revolutionary, promising to fundamentally change our capabilities across so many fields: energy, materials, computing, propulsion. However, it's crucial to temper that excitement with the reality of the enormous practical and experimental challenges involved.
Right, understanding is one thing, building is another.
Exactly. But let's dream for a moment. First, imagine entirely new energy sources. We're not talking subtle improvements on solar or wind. We're talking about tapping into unconventional energy release mechanisms. Perhaps the direct conversion of hypergravity, coherence itself into usable energy.
Energy from the vacuum. Or from hypergravity.
Something like that. Not fission, not fusion, but potentially harnessing a more fundamental, pervasive energy field. If achievable, it could offer clean, limitless power, completely transforming civilization and solving energy crises overnight.
Think of a device drawing energy directly from the fabric of space-time itself.
Limitless clean energy.
Okay, that's the holy grail. What else? Then there's the potential development of coherence-laced materials. Materials specifically designed not based on atomic chemistry, but engineered to interact directly with these hypergravity coherence fields.
And what could they do?
The applications sound like pure sci-fi. Potentially enabling warp drives for genuine, faster-than-light travel by manipulating space-time, unprecedented energy manipulation capabilities, advanced computational substrates that make silicon look like an abacus.
You mentioned warp drives before, based on these materials.
That's the implication. Or materials that are perfectly temperature invariant, never degrading, perfect for building interstellar probes that last millennia, or habitats in extreme environments. Materials whose properties derive not from chemical bonds, but from deep hypersymmetric structures.
Okay, what else?
This framework could also, potentially, lead to crucial quantum gravity applications. It might provide the missing insights needed to finally unify general relativity, our theory of gravity, and quantum mechanics, our theory of the small. Understanding how matter and gravity emerge from hypergravity could be the key to that theory of everything physicists have sought for decades.
The key to unifying physics.
It could be. On a more practical level, think about advanced sensors. Materials with these predicted hyperdimensional electromagnetic properties could be used to build detectors sensitive to higher dimensional phenomena, or capable of picking up incredibly weak signals currently lost in noise.
Seeing dark matter, maybe, or other exotic things.
Potentially. It could revolutionize astronomy, maybe allowing us to map dark matter directly, or dramatically enhance medical imaging, security scanning, environmental monitoring, peering into realms previously hidden from us.
And communications.
Right, revolutionary communication systems. Imagine exploiting hyperdimensional frequency multiplexing, transmitting vast amounts of data across multiple interwoven dimensions simultaneously.
More bandwidth than we can dream of.
Essentially instantaneous global communication, or maybe even viable interstellar communication networks, making our current internet speeds look utterly primitive.
Okay, that's huge. And you mentioned superconductivity.
Yes, perhaps one of the most exciting, near-term, relatively speaking, prospects. The possibility of superconductivity at room temperature.
The other holy grail. No electrical resistance at normal temperatures.
Exactly. Lillian's framework suggests this might be achievable by leveraging hypergravity coherence to somehow stabilize the quantum state that allows electrons to flow without resistance, but without needing cryogenic cooling.
The impact would be enormous.
Transformative. Revolutionize power grids by eliminating transmission losses, enable incredibly powerful, efficient motors, electronics, medical scanners like MRIs without liquid helium, and widespread magnetic levitation for transport. It would change everything.
These possibilities are just breathtaking. Almost feels like magic. But as you said, the challenges must be immense. How do we even begin to detect or create something that operates on these principles, something beyond our current physics? It feels like trying to grasp smoke with tweezers.
The challenges are as immense as the potential rewards, absolutely. First and foremost, just exploring non-periodic matter requires entirely new types of instruments. We need detectors sensitive to these proposed coherence fields and hypofractal layers.
Our current detectors won't work.
Our current detectors are designed to sense electromagnetism, gravity as we know it, nuclear forces, the standard interactions. We need fundamentally new ways to see or touch these deeper structures. Maybe technologies that can somehow probe higher dimensions or detect subtle fluctuations in hypergravity coherence. It might involve entirely new sensor principles, unlike anything we use today.
Okay, new tools. What else?
Secondly, it demands new theoretical models.
Yeah.
We need to flesh out the mathematics. While Lillian provides this profound HHCR-TOE framework, we need a complete predictive theoretical apparatus. Robust mathematical models that make precise, testable predictions to guide experiments.
More than just the concepts.
Exactly. This isn't just tweaking the standard model, it's potentially building a whole new language for physics, integrating hypergravity and hypersymmetry dynamics. It requires a huge conceptual leap.
A new language for reality.
You could say that. And finally, it almost certainly necessitates experimental conditions that push boundaries far beyond what we can currently achieve. Boundaries of energy density, coherence control, perhaps even dimensional access.
Bigger colliders. Something else.
Maybe even more powerful high-energy colliders than the LHC, yes. But perhaps also entirely new kinds of facilities. Lillian's work hints at concepts like hyperdimensional laboratories places, specifically designed to create environments where higher dimensional interactions could be generated, probed, maybe even manipulated.
Hyperdimensional labs. Okay.
It's definitely a long road ahead. It will demand unprecedented levels of international collaboration, funding, and sheer scientific ingenuity. But the potential discoveries are arguably the biggest imaginable.
This entire theoretical framework, HHCR2, and the very idea of matter beyond the periodic table, it really does redefine our fundamental understanding of the universe, doesn't it? It goes way beyond just practical applications in technology, deep into philosophy, into the nature of reality itself.
It really does. And this raises that crucial question. If we seriously consider the broader implications, the very existence of matter beyond the periodic table fundamentally challenges our most basic scientific and philosophical concepts. It forces us, or should force us, to reevaluate what we thought we knew about reality.
How so? What are the biggest philosophical shifts?
Well, firstly, it really reinforces and deepens that concept of matter as emergent. It hammers home the idea that matter might not be composed of fundamental particles in the traditional sense, not immutable building blocks, but rather, it emerges. It's a phenomenon arising from deeper invariance, like this proposed hypersymmetry coherence.
So the solid world around us is a manifestation.
A manifestation, a projection, a stable pattern, emerging from something far more profound, more abstract, perhaps more mathematical or symmetrical. It radically blurs the line between physical existence and underlying pattern, between permanence and dynamic process. What we perceive as tangible stuff, including ourselves, might be ripples on a deeper ocean.
That's a profound shift in perspective.
It is. And this naturally leads to redefining physics itself. The HHCR2, if correct, necessitates massive extensions or even replacements of our existing gauge symmetries and quantum field theories. Physicists would need entirely new mathematical frameworks.
Whole new physics.
Potentially. It fundamentally redefines the relationship between forces, particles, and spacetime, proposing they are all interconnected and ultimately derived from a more unified, hypergravitational foundation. Our incredibly successful standard model would become just a specific, limited case, a low-energy approximation describing only a fraction of the universe's true complexity and potential. Like realizing Newtonian gravity is just an approximation of general relativity.
Like finding out the game we were playing was just level 1.
Exactly like that. Realizing the rulebook is vastly larger and more complex than we ever imagined.
And okay, what about those truly mind-bending implications you touched on earlier? Our sources mention consciousness and alternate universes. How could those possibly fit into a theory about matter and hypergravity? That really stretches the imagination.
It absolutely does, and we're firmly in speculative territory here. But it's fascinating speculation grounded in the framework's logic. A truly provocative thought Lillian raises is that certain exotic forms of matter might be intimately tied to the emergence of consciousness and intelligence.
Conscious matter, like the matter itself is conscious.
Not necessarily the matter itself in the way we think of rocks or tables, but the idea is that certain complex, highly coherent configurations of non-periodic matter, perhaps leveraging these hyperdimensional properties or resonance loci, might be uniquely suited to act as substrates for advanced cognition or fields of intelligence.
So not just brains like ours.
Perhaps not. Maybe consciousness isn't limited to biological brains running on electrochemical signals. Perhaps it can emerge in entirely different physical systems, maybe in stable, coherent fields or structures made of this exotic matter. Could consciousness itself be a state of hypercoherence within these deeper layers of reality? It's a question that challenges the very definition of life and thought.
Consciousness as a physical state of exotic matter. That's whoa.
It is whoa. And then, pushing the speculation even further, there's the implication for alternate universes.
Back to the multiverse idea.
Yes. Lillian suggests, following the logic of HHCR2, that if other universes exist and if their fundamental constants derived from hypergravity reductions are different.
Their matter would be different.
Entirely different. Their fundamental matter structures, the types of particles, the forces, the resulting chemistry, it could all be completely distinct. They might adhere to entirely unknown periodic tables based on rules utterly alien to us.
So our universe, our laws, our matter is just one possible outcome.
One possible outcome among potentially infinite variations, each representing a different way hypersymmetry can reduce or manifest. It's the ultimate perspective shift, seeing our entire familiar reality as just one possibility within a vast, almost unimaginable cosmic landscape of potential universes. A humbling thought indeed.
Wow. What an incredible deep dive this has been. Seriously. into the possibilities way beyond what we thought we knew about matter, from understanding the limits, the known limits of our periodic table, to these absolutely mind-bending concepts of hypergravity coherence, higher dimensions, emergent reality. Lillian's HHCR truly offers a completely new lens, a new way to view the entire universe. It's like realizing the world isn't just the flat map we learned, but this incredibly complex, multi-layered, maybe even living sphere, full of hidden depths and unseen connections.
Absolutely. And this profound framework, Lillian's HHCR, it provides a coherent, albeit very complex, way to start thinking about phenomena that standard physics currently struggles mightily to explain. Dark matter, dark energy, maybe even consciousness.
Right.
It's a powerful reminder, isn't it, that our scientific journey is so far from over. That the fundamental nature of reality just keeps unveiling more and more layers of unexpected complexity and, frankly, unexpected wonder. It really challenges us to constantly question our deepest assumptions, expand our conceptual horizons, and dare to imagine what might lie just beyond our current scientific boundaries.
So, thinking about all this, what does it all mean for you listening right now? If matter itself, the very stuff you're made of, is potentially an emergent phenomenon influenced by these deep hidden symmetries and this underlying hypergravity, what does that imply about the fundamental nature of reality all around us? And maybe even more profoundly, if consciousness itself could be tied to these exotic forms of matter, these coherent states, what does that imply about the nature of consciousness, your consciousness? It gives you a lot to mull over, doesn't it?
It certainly does.
We really hope this deep dive has sparked your curiosity, maybe stretched your mind a bit, and provided you with some truly unique insights into the frontiers of physics and cosmology. Until next time, keep exploring, keep questioning, and stay well informed.